If C is a circle with a radius of 4, centered at the origin, evaluate the given line integral. Notice the integral symbol has this circle in the middle, which indicates the curve C satisfies Green's theorem, which will make it much easier to evaluate this line integral. For review, Green's theorem states if C is a simply connected piecewise smooth curve with a positive or counterclockwise orientation that encloses a region R, and if the vector field f has components little f and little g that have continuous first-order partial derivatives, then the line integral can be written as a double integral over the region R. And again, when the path of integration satisfies Green's theorem, we denote the line integral, as shown here, where we have a circle in the middle of the integral symbol. So going back to our example, we know the curve C has a positive orientation. Looking at the differential form of the line integral, we know the vector field has an x component of 3y minus e raised to the power of sine x, and the y component is 5x minus sine of the quantity y cubed plus y. Which means for the formula shown below for Green's theorem, little f is the x component, and little g is the y component. And now let's find the partial derivatives. We first want the partial derivative of g with respect to x. And we'll notice the partial derivative of g with respect to x is just equal to 5 because we differentiate with respect to x, treating y as a constant. We also want the partial derivative of f with respect to y. Looking at f, we have 3y minus e raised to the power of sine x. The partial derivative with respect to y is just 3, again because you treat x as a constant. Which means the given line integral is equal to the double integral over the region R of, notice how this difference is just 5 minus 3, which is equal to 2. Then we have differential A, and the region R is this region here, and because the region R is a circle, it'll be easier to evaluate this using polar coordinates. When using polar coordinates, differential A is equal to r dr d theta, which means this is equal to the double integral of 2r dr d theta. And now let's determine the limits of integration. Because the radius of the circle is 4, the limits of integration for r are from 0 to 4, and then to go all the way around the circle, the limits of integration for theta will be from 0 to 2 pi. This double integral is much easier to evaluate than the original line integral. Let's evaluate this on the next slide. We first integrate with respect to r, which would be 2 times r squared divided by 2, which simplifies nicely to r squared. And now we need to find big F of b minus big F of a, which is 4 squared minus 0 squared, which is 16. And now we integrate with respect to theta, which is just 16 theta. And now we find big F of b minus big F of a one more time. We have 16 times the quantity 2 pi minus 0, which is 2 pi, which gives us 32 pi as the value of the double integral, which is also equal to the given line integral. I hope you found this helpful.